for the afternoon session. Our first talk is going to be Szymon Peszat from Krakow, and he's going to talk about regularity of solutions to linear SPDEs driven by Lévy processes.
Okay, so I would like to talk about time regularity of the solution to the linear equation. So dx is, say, ax dt plus dz, and z is a Lévy process. In a Hilbert space U. A is a generator of a semigroup, so A generates a C0 semigroup. S on a different space H on H, and usually H is the smallest, is a subspace of U. So we assume that H is smaller, and we are interested in the condition under which X as a process in H is continuous or Cadillac. So of course we have to assume that the semigroups acts from U to H. So we assume that ST L U H for any t. And as I said, I'm interested in the problem that, so under some condition, which is not very difficult to find, that X takes values in H, but I'm interested in the regularity in time. So whether X is Cadillac. Or in Gaussian case, of course, continuous. Or in Gaussian case, continuous in H. So I would like to start with some tools. So the first quite general tool is the cotyledons. And cotyledon says that if U is H, so if U is H and S is contraction, so and S T is omega T. Omega is not necessarily negative, so omega VR. Then X is Cadillac, or continuous if Z is continuous. Then X Cadillac in H or continuous. And the argument is quite simple. I mean, this is the argument is not the original cotyledons proof, which was quite difficult, but I will mention the ideas of Erika Hausenblas and Jan Seidler. So they used the notch dilation theorem. And this theorem says that there is a Hilbert space H script, so it's a Hilbert space, and there is a group of strongly continuous group, so T is a group on H, and there is also a projection P continues from H to H such that ST is P dt. So if we have this, we can study regularity in a very simple way. Why? Because xt is of course given by the variation of constant formula, so it says st minus s dzs, and that's, for simplicity, I assume that x0 is 0. So x0, 0. That's, I can do it, of course, without any loss of generality. So if I have this formula, I can write something like this. Dzs. Right, and usually this is a stochastic integral. It's not a convolution. So it is Cadillac or continuous in H script. Right? And now I act by something which is regular, quite regular. So everything is also Cadillac in H script. But P projects from H script to H, so anything is Cadillac in H. So it's a very simple. And in the same way, one can prove the maximal inequality. So it's a very simple and nice argument. And based on the quite general theorem. So the maybe that's not a good idea. Sorry. The next possible tool is, because what is the drawback of this approach? I have to assume that the semigroup is contraction. This is probably not the worst assumption, but unfortunately I have to assume that U is the same as H, so the noise lives in the space when I'm looking for the solution. And usually in the say case of the cylindrical noise, we would like to have U noise on the much bigger space, like in space-time white noise in inner case. Okay, so that this method doesn't work, the different tool can be applied, and this is, I think, the Prato Kvaping subject factorization. And what is behind of this, there are two facts. One is an elementary analytical fact that such integral minus alpha r alpha minus 1 ds is constant. It does not depend on r or t if alpha is from 0, 1. So it's constant. And the second is the Fubini, that we can interchange integration stochastic and deterministic. So if we have these two, this plus Fubini, what we have that xt is the same as, we write jy of t, where what is y? Y is the integral over 0 to t minus s to minus alpha s t minus s dzs, and j is a operator, it's a deterministic. It acts on the trajectory, so phi t is some constant depending on alpha, which is known but doesn't matter, 0 to t minus s, alpha minus 1, s t minus s, phi s ds. So we have this representation, and of course we have some extra singularity right here. But it helps because, at least in some cases, why? Because it's easy to see that J is a bounded linear operator from LP 0 to Th into C 0 to H, provided that P is large enough. What is the condition for P? Of course, we would like to use the Hölder inequality. So the condition is, of course, that P star, the adjoint alpha minus 1, bigger than minus 1. If we have this, we can use Hölder, and not difficult to show that. Instead of C, we have L infinity. That's obvious. But we can prove that C also. That's a bit more demanding. Okay, so that works for Wiener process quite well. Unfortunately, it doesn't work for Lévy. Of course, the formula is still valid, provided that everything is integrable. But what we have to check this. Of course, that cannot be true, because we knew that the Lévy process is not continuous on only Cadillac, so something must be wrong. So what is wrong? If I calculate in the Wiener case, I need something like this: yt to power p integral 0 to t dt. Right? So if this is finite and p is such that we have this, that's perfect. And of course, for the Wiener case, we have what? We have the expectation of the p norm of the p power of this is something like some constant depending on p integral 0 to t minus s to minus 2 alpha norm of st minus s. In the Wiener case, it is the Hilbert-Schmidt norm from u to h, but okay, that's some Hilbert-Schmidt norm to power 2 ds and p over 2. And then, of course, we have dt. And that's what is nice, that we have p over 2 outside of this. So what is really needed, that this integral is finite. But in the Lévy case, of course, we are forced to go with p inside. and we have something like integral 0 to t minus s minus p alpha times something. And of course, p alpha must be bigger, must be smaller than 1. So minus p alpha bigger minus 1. Oh, sorry. Yes, that's okay. And that contradicts to this. So it doesn't work. It works for, it would be interesting to find a different condition, because I would like to replace C by Cadillac. And maybe I would like to find the inverse of J and check something much easier, but I don't know what. So that's possible, but I don't know how to apply it. So the third tool, an interesting result, is basically for Gaussian only, but because if Z is Gaussian, then of course S is Gaussian. So a priori we have a theory due to Fernic-Talagrand, and which translate me the regularity, I mean, describe the regularity of the Gaussian process in terms of the covariance. So what they, actually there was a paper by, I should maybe give the reference. Oh, yes. It's the paper by Isco, Marcus, MacDonald, Talagrand. It's 5 authors run. Azine, right. Later we will be a paper by 6 authors, which is certain improvement. And what they studied the diagonal case. So the xk is some minus ak xk dt plus bk dwk. And of course, ak and bk are some real numbers, and wk are independent standard Brownian motions, one-dimensional real values, of course. And they were interested in the continuity in L2. Of course, the condition under which x is xk lives in L2 is quite simple. Is that sum of bk square over ak is finite. I assume that ak are positive. So this is the condition, if and only if condition under which x lives in L2, and the question is it sufficient for the continuity? And the answer is interesting, is not. So there are two claims. The first claim is the following, that if x lives in H and this sequence is bounded. So, and supremum over k, bk is bounded, then x continues in H. So this is the first claim. The second claim is, so this is at least the claims which I understand from the paper. The paper is not very, I mean, it's quite difficult. So the second claim is that there is a sequence AK and there are sequences AK and BK such that X lives in H, so we have this, but X is not continuous. So there is a AK, BK, X lives in H, but it is not continuous. So we can use the first claim to generalize a bit the statement. So instead of the diagonal case, we can prove the continuity for the linear equation with a under the assumption that the semigroup is analytical. So if I have this equation, so AT analytical and W is cylindrical on H. Then if X lives in X in H, then X is continuous. And the argument is very simple and can be derived from one. I learned from this from Wodek-Smoleński. And I think that some details are also in the paper by Animier and Smoleński from, I think, 2. And the argument is the following, that we can look at the law of X. So this is the law of X in the space of trajectories. So the law of X in L2 0T H. So if X lives in H, then it is square integrable in H in the same sense. So this is the measure on L2. And the question is, of course, whether the support of this measure is C. So the question if Lx is in C 0T H, right? That's the clear statement. And we know what is the reproducing kernel or Cameron-Martin space of this measure. It is now, in the book by Daprato and Zabczyk, it is very often used. This fact that the reproducing kernel of Lx is the space of all trajectories with some controls, but in the case where the generator, the semigroup is analytical, is exactly W12 0T H times L2 0T dA. So that's the formula. That's known. So what is, so we have this and we have this. And how to, mix them? What is enough? It is enough to find a self-adjoint generator with the same domain as a given analytical domain generator. If I have this, I have more or less the same reproducing kernel. But the regularity depends only on the reproducing kernel. So this is not difficult. So I have this is my generator for analytical semigroup. I need to find a self-adjoint operator with the same domain. It's a very simple construction, at least in the compact case, because I mean the inverse of A is compact, of course. So one can generalize this. Okay, I think that. Well, I don't know how to use this idea for the Lévy. There is some hope, but at this moment there are no progress. So let's go back to the Lévy case. In the Lévy case, there are more counterexamples than positive results, really. So the first is very simple counterexample. So I have a Lévy process in U, and U is bigger than H, so U is strictly bigger than H. And assume that there are no Wiener part. That's for simplicity. Okay, so there is a Lévy measure of Z. So mu Lévy measure of Z. And usually it is a measure on U. It's natural. It's a measure on U. So I assume that it's really on U, not on H, so that this is positive. So there are jumps from of the size not from U, but not from H, but from bigger space, which is it seems very natural situation. Actually, we'll see later whether it is natural or not. Okay, so we have this situation. Then X is not Cadillac in H. This is the very simple conclusion. So the solution cannot be Cadillac. With some, with Cadillac means with probability 1. Why? So for simplicity, we assume that measure is finite. So in fact, Z is a compound Poisson. Z is a compound Poisson, and with positive probability. So let's fix a time interval, so 0t, and with probability, positive probability, so with positive there is a jump of the process Z, the jump of the process Z in the interval 0t of the size not from H. So there is a Z has the first jump in 0t of the size Z tau not from H, right? That's a consequence of this. So if we add this, then what is X of t for t bigger than tau 1. So that's simply as t minus tau 1 set tau 1. And of course, the norm of xt in H, it could be finite. I mean, for any t positive or different from tau 1. But if we calculate the supremum over is plus infinity, because there is an element which is from U, not from H. So it's a very simple argument. And so the trajectories are not Cadillac, not continuous, no, not bounded. Okay, so if you would like to have something interesting, some interesting situation, we have to reduce our situation to the case where the Lévy measure is in H, unless the answer will be too quickly. Okay, that's still. So maybe I will. Okay, so we are interested in the situation where Z in U, but mu of U minus H is 0, right? And the question is, can we find an example of a Lévy process living in a bigger space with jumps only from the smaller? And is it interesting or not? Right? Because if Z lives in H, we can probably use coterminals. So we don't have to investigate this case. And there's a very natural situation when Z lives in a really big space, but jumps are from the smaller. So let us consider two different one-dimensional Lévy processes. So let us Z1, Z2 independent real Lévy. So if they are independent, it means that they can jump, of course, but not simultaneously, right? So if I look at this process, it's a pair. What is possible jump size of this process? So it means that they cannot jump simultaneously, so the jump size of this is not allowed. Only this jump or this jump are allowed. So the jump measure of this is concentrated on axis, right? Okay, so if I consider the sequence of independent Lévy-Nossis, so now I have Zk independent Lévy process, and I would like to study this in the space L2, so this is my space H. Then, of course, the jump measure is concentrated on the sum of axes, and the sum of axes is a set sum, not an algebraic. Is of course the subspace of L2. But for example, if Zk are of the same, I mean the same distribution, then of course Z is not cannot be a process living in L2. So that's at least maybe not. Oh, it's a natural example of that process, Lévy, taking values in a big space, but with jumps in a small. As a state space as U, one can take some weighted space. It's not with weights going to 0. Sorry, that's U. Okay, so the question is, can we show the Cadillac property of X of the solution in this case? So at least there is a hope so far. And there is a counterexample. So I start from counterexample. So I promise paper by 6 authors. It's a very short paper. It's like 4 pages. But because there is a huge, the address list, it makes a lot of. So the authors are Brzeźniak, Gaudis, Peter Imkeller, myself, Enrico Priola, and Zabczyk. And what we, maybe I will not give the whole result. I just restrict to the case when we have this situation ak xk plus pi k, where pi k are independent Poisson processes with the intensity 1. So pk Poisson. With one, each with intensity 1. Okay, so again, the condition under which X lives in L2 is something like the sum of 1 over ak is bounded. This is it's not very difficult to find that this is a condition. Of course, the process Z cannot live in L2. Right, because what? We have the ak square of t, probability that this is plus infinity is 1, right? For any t. Because there are infinite many ones in the sequence. So it's obvious. So that is not a process in L2. And the answer is, of course, that X is not Cadillac, fortunately. So X is not. So, in fact, with probability 1, at each point there are no limit, right and left limit of X. And the argument is also very simple. We have this xt minus xs, obvious estimate that this is bigger than xk t minus xks for any k. Right? That's and all t and s. So if we calculate the oscillation of, the oscillation is something like supremum s from t. So I should fix omega and some times t omega and calculate it. I should write maybe this on omega. And I calculate the oscillations, so t omega minus delta t omega x t omega omega minus xs omega. Then, of course, if there is a left limit, then this supremum goes to 0 as delta goes to 0. So that's the limit. Delta goes to 0 is 0, provided that there is a left limit. It's a Cauchy condition. But this is what? But this is bigger than this. And in this interval, there's at least one jump of this process. So it's bigger than 1. So there are no limit. The same is with right limit. So, of course, we have another counterexample. Okay, so now I would like to say something about the what we can modify in this example. Probably we can modify taking the multiplying by something which goes to 0, or changing the intensity, decreasing the intensity, such that this is still true, but there is a hope that, but we cannot use this argument. So is it possible? I think that yes, but at this moment I have only a partial answer. So I would like to start the weak Cadillac property. So for simplicity, we assume this minus ak xk dt plus zk. Ak are positive, and zk are independent. Lévy. Zk has Lévy measure mu k, and I assume that there are moments, 4 moments of this measure. So mjk is integral x j mu k dx. It's finite from j 1, 2, 3, 4, and of OK. So of course, in this previous case, what we have, the measure mu k is just d1, delta on 1. So of course, these numbers are the same, they are not ones. Right, so, and I would like to answer the question whether xt u this real valued process is Cadillac or not. For sufficiently large class of U, especially I would like to show that this process is Cadillac for any U from a bigger space than L2. I can show this, actually, that there's a Cadillac version of this, which should give me the Cadillac property of X, because for U in some bigger space L2 beta, such that this embedding is compact. So that's my construction, but there's some delicate problems. So maybe I will talk about this later. So what is the tool? How one can study such problem? So there is a quite classical version of the Kolmogorov criterion. Yes? Everybody knows the Kolmogorov theory, right? That regularity. So what is the version for the Cadillac processes? Now, it's not something like this, that if psi is a separable real process such that there are epsilon and p that t minus psi t minus h psi t minus psi t plus h less than some constant. So that's k h to power 1 plus epsilon. And that should be for all t from 0 to t and h such that t plus h and t minus h is from 0 to t. So if we have this, then psi is Cadillac. Actually, it's not necessary for the real valued processes. It's for processes taking values in a metric space. But I mean, I would like to apply this for psi of this form, so I don't need a generalization. So okay, so if we have this, then psi is Cadillac or has a Cadillac version. And also we have the estimate for the moment. So we have that supplimum So I have the I should write theta, t, and s. Psi t minus psi s to power q less than some constant c e psi 0 to power q plus 1 for any q less than p from p. So we have this. And I would like to use this criterion to this process. And the theorem is the following. Is something wrong? No. Because yeah. So I need some time for the formulation, but that is enough. So with epsilon from 0 to 1, we associate certain and sequence bk is positive. We associate certain bk should be a weight. I will show the weak Cadillac property of x in L to beta. That's my goal. So of course, what bk should go to 0. That's my interesting case. But I can formulate for any sequence. So I have this, and I have some formula, and the leading term, I will skip maybe something different. So it's bk to minus 4 eta k, eta 4, n for k, n is the moment of the mu k plus m2k square, and I have eta 2k to power epsilon minus 1 plus ak epsilon minus 1. Actually, it's not everything, but it's the something which is the most important part of this. So let's keep it this. And the theorem is the following. Assume that the first condition is exactly the condition under which x lives in L2. So assume that, I mean, it's quite integrable process in L2, that m2 of k over ak plus n1 square of k over ak square is finite. So assume this and let bk be a sequence of numbers strictly positive such that a epsilon of beta is finite. Then for some epsilon. So if I have this, then for all z from L to beta, this process xt z in L2 is well defined and Cadillac. So this is the result using this. I mean, this criterion one can prove the proof is quite technical, but I think it's correct. So maybe I will finish now.
go back to the beginning of your talk with the cutter lens method, you
Yeah.
needed the semigroup ST to be a generalized contraction.
Mm-hmm.
Now, the difference between the norm of a generalized contraction and the norm of an arbitrary C0 semigroup is just
One.
yeah,
One
it's a
term.
number. So,
Yeah.
is there any possibility of generalizing the technique?
So this is the
Yeah.
estimate for the
Yeah.
any semigroup. Well, it makes a big difference, in fact.
Yeah.
But
And the difference is that you cannot do iteration.
Okay.
exactly.
Okay.
If you're willing to turn your Hilbert space into a Banach space, you can
Yes,
always
I
pick a
can.
constant one.
That's true. Yes, I can change the norm on my Hilbert space, but actually I don't know whether there's a dilation theorem on Banach spaces.
Very special.
Unfortunately, there are no. So
Positive. Then
yeah, so that's the same. One cannot avoid this way. I think that what one can add something that Z can be a process not in H but in H script, right? That's the method works. Unfortunately, the description of H script is very artificial in a sense. So I don't know how to, express this this in the reasonable condition of a process. Yes, because if we go back to the equation is this p dt integral 0 to t p minus s dzs. So what I need in only that this is Cadillac in H script. So I don't need to assume that Z is in H, but it could be in H script. So that's possible. But I cannot conclude anything interesting from this observation.
Any other? Let's thank Szymon again.